Testing my audio, test, test, test. As we build our picture of structure of an atom, the electronic structure of the atom, and we're taking a more modern look at it now that we've moved past uh, Bohr's model of the atom. I want to come back to that critical piece of Bohr's model, which is that it explained the emission spectrum of hydrogen. And this is this observation that gives us a lot of information about the structure of the atom. And so any model we have has to be able to explain it. And so I'm gonna walk through now how we explain it in a modern picture of the atom, where we've established that the Schrodinger wave equation solves, or we can mostly solve, for pieces of information about the shape and the energy level and the orientation of space that the electron is probably going to occupy. And so using those quantum numbers, we can now apply that to this idea of emission spectrum for different elements, and that we see these very specific wavelengths every time. And it's this characteristic thumbprint for an element. So so here's kind of a written summary. I'm going to use a picture on the next slide to talk through this exact thing. But what we're going to be seeing is that each wavelength in a spectrum, an emission spectrum for an element, is going to correspond to an electron transition between the orbitals. And so we've got our let's say our nucleus, or our atom. We've got a nucleus somewhere down here, and we have energy levels for our electrons that they can occupy, where n equals 1 is our lowest energy space or energy level that an electron can occupy. So if we had an electron at that energy level and it absorbed energy through heat or light, it would become excited. Now, excited is the word I would use to describe my kids when I gave them a little sugar. So I'm going to run a parent-focused analogy alongside this, and it might help two of you. So the electron gets energy, and it say it's heat or light. Or the 3-year-old was given Halloween candy. All right. So it gets more energy and it is excited into an unstable state. So for that electron, it means it's getting promoted into an energy level of N that is less stable. It's higher in energy and it's further away from the nucleus. That's where that instability comes from. It is further away from the nucleus, and that negative and positive opposite charges are attracting each other, and that's a stabilizing factor. So the further away you get, the less stable you are. All right. So the kid with the Halloween candy, the 3-year-old, he's now running around on the couches, jumping and screaming, right? He's at an unstable state. This could get hurt at any minute. All right. So now it's at the higher energy level. The electron can't maintain that unstable position. It's not energetically favorable. And so it will relax back down to a lower energy level. And we use these terms excited and relaxed, not in the way we would in our common day-to-day language, but relaxing here means an electron goes from a higher energy level to a lower energy level. The 3-year-old can only maintain is like running around screaming, jumping on the couches for so long before they also get tired and they need to relax, and they fall into a pile of stuffed animals or like in the cozy corner. Okay. So now we've come down a level. Now the difference between the jumping on the couch kid and the cozy corner kid is the same as the energy level difference between being at the unstable n equals 3 to the slightly more stable n equals 2 state for an electron. So that electron lowers its energy level, it jumps down, and it can't go anywhere in between. Because it's quantized, it means it can either be at n equals 3 or n equals 2 and nowhere in between. And so that means that the energy difference between those two levels is going to be released as energy that's light. That energy goes somewhere, right? For the toddler, that energy is going into the heat the kid is producing, the friction and force on the poor couch cushions as they're getting trampled. And as that energy dissipates as heat and as destroyed couch cushions, they end up at the lower energy level, the cozy corner. And the electron, as it drops down in energy, it's going to release that energy that kept it up here, and now it wants to be down here. It's going to release it as light, as a photon of light. And that wavelength for that photon of light is going to correspond to the energy difference between those two levels. So that means the energy of a photon being emitted by a element that was heated or absorbed light will correspond to the energy difference between our n levels in our structure of our atom. And that gives us a ton of information about the structure of that atom. It tells us where those energy levels are for that electron or any electron within it. So let's look at hydrogen. It's our simplest atom that we can look at, right? It's just a proton and an electron and nothing else. So we like to use it as our kind of testing grounds for these ideas. So looking at hydrogen's energy transitions, that will predict the wavelengths of light that we observe after the hydrogen has been heated. So, or an electrical current is passed through, like in a hydrogen lamp, like we saw in our picture earlier. And so we can predict those energy level or those wavelengths of light by looking at the energy difference between the energy levels and calculating what that value is. So for any electron at an energy state n, and so let's say it's at n2, then there are n-1 energy states which it can transition to. So if it's at 2, it can only go to 2 minus 1, 1. It can only transition down to n equals 1, right? And so we're thinking about the electron after it has already been excited. So it's excited up to some other energy level, and it can then relax to any of the states below it, any of the n levels below it, but not the one it's in. That wouldn't really be relaxing. So it will generate n-1 lines if it's excited up to an nth state. Now, the energy that is released by that photon is going to be the energy difference between the two. And so we're going to be able to we'll be able to measure the wavelength that the photon escapes at is going to tell us the energy of that photon, right? Remember, we talked about how the energy of a photon is equal to our Planck's constant times the speed of light divided by the wavelength. So we can correlate these two together. So if we calculate that energy of the photon from the observed wavelength, we then know that the change in energy for that electron, and it'll be equal to the opposite. So we can calculate this. We know already that we can relate the energy level of a photon to the integer, the inverse of the integer of that quantum number n. And so here, let me write that down on the side too. We had said that the energy of electron at a level would be equal to that Rydberg constant, that negative 2.18 times 10 to the negative 18th joules, and then 1 over the quantum number n squared, the inverse of the quantum number squared. And so that's all we're doing here to figure out the energy of that photon, is we're taking the energy difference between two levels. And so this right here is the final state minus the initial state. And so we easily can measure this energy of the photon, and we can measure what the wavelength is. And that then allows us to figure out what these energy levels were, or the difference in energy between them. And so we can simplify this right here. And this is kind of the version to keep in mind and keep in your notes and keep handy. That relates specifically this wavelength to our final and initial energy levels. So let's look at this for hydrogen. So we have an electron at the n equals 1 energy level, and if we input energy into it, it can increase up to a number of energy levels. If we make it up to n equals infinity, we're saying that we've ionized that the atom, right? We've removed the electron from the sphere that it can be attracted to the nucleus. It's so far away from it, it's not attracted to the nucleus anymore. And so that requires a lot of energy, right? That requires, in fact, the binding energy of the electron. See? Okay, so let's say it goes up to n equals 5, right? So we're looking at this energy level right here. Now that electron can relax to the n equals 4 or 3 or 2 or 1 energy level. And so we start to see all these different transitions that are possible. Like you can figure out all the different combinations. There's a number of combinations where it relaxes all the way back down to the n equals 1 energy level. And there's a number of combinations that go from n 5, 4, and 3 down to the n equals 2 energy level. And then we have some that go just down to the n equals 3 energy level. And when we look at these and compare them, the energy of the photons released, if it goes all the way down to n equals 1, will be much larger than the energy of the photons released if it relaxes down to a energy level higher than n equals 1. And this difference in that energy of the photon will correspond with different wavelengths of electromagnetic radiation. And so for these larger transitions or relaxations, these larger energy differences, we won't be able to see them with our eyes. They'll be in the ultraviolet wavelength range. And the really small transitions over here, where it's just going between a couple of the higher energy levels, those we're not going to be able to see either, because the energy of the photon will correspond with a wavelength that can be found in the infrared region of electromagnetic spectrum. But some of them, the ones in particular that go to n equals 2, will produce an energy of a photon that will correspond to a wavelength that we can see in the visible region. And these are the wavelengths of light that we see when we heat hydrogen gas. And so we can explain what we're observing with this model. And we can also explain some stuff we can't observe, but we can with our eyes, but we can detect with instruments, and confirm that this is how these energy transitions take place. And it allows us to map out the energy levels for the electron within the hydrogen atom. And then we can do this to other atoms and molecules. And so here's how we would calculate it, right? So let's just take one of these. Let's focus on this one I've circled here in red. We're going to go from an n equals 2 excited state and relax down to the n equals 1 state. So to determine what the energy of the photon would be, which can help me understand the wavelength, I would plug into this equation right here, that the energy of the photon is equal to that Rydberg constant times the difference between the inverse square of quantum number and final and the inverse square of the quantum number and initial. So that final one, since we're relaxing down, is the smaller number. So that final one will be the smaller n value. So what I would plug in to calculate the energy of that photon for that transition is my 2.18 times 10 to the negative 18th. And then I would have that all multiplied by the inverse of n equals 1 squared, then minus the inverse of the n equals 2 squared. And taking that value, I'll get an energy of a photon that corresponds to 1.635 times 10 to the negative 18th joules. All right, I could then take that a step further and figure out what the wavelength is, right? Because that energy of a photon then is equal to that Planck's constant times the speed of light divided by the wavelength. So if that's equal to 1.635 times 10 to the negative 18th joules, I can come in here and write this out. I've got my speed of light. I've got my Planck's constant. And I divide that by my wavelength. My wavelength that I'm going to get will be I get a wavelength of 1.216 times 10 to the negative 7th meters. If I convert that into nanometers, because I think about light in nanometers, and maybe you don't have that kind of habit yet, but that's why I'm going to think about it this way. I'm gonna convert this into nanometers so I can compare to things like that visible spectrum of like 400 to 700 nanometers. So I have 10 to the 9th nanometers for every 1 meter, and then I get a value that is 121.6 nanometers. So my wavelength is going to be at 126 or 121.6 nanometers, which is smaller, a smaller wavelength than I'll be able to see with my eye, which can see about 400 to 700. So So that's how we can predict the wavelengths that we see, and how we can take information about a wavelength and learn about the difference in energy that produced that transition.